tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, good evening and welcome everyone to Mount Washington Observatory's Science in the Mountains lecture series. My name is Brian Fitzgerald and I'm the Director of Education here at Mount Washington Observatory. And joining us this evening to share updates on current research at the observatory here are Summit interns George Mousmoules, Jacob Garside, Joshua Elms, and Maya Hartley. Thanks so much for joining us for tonight's program. For those of you who are not already familiar with the observatory, we are a nonprofit, member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. And the way that we accomplish that is through operating our Summit weather station with around-the-clock weather observation and forecasting, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have questions at any point for tonight's speakers and you're joining through Zoom, please make sure to use the Q&A button. You can find that at the bottom of your Zoom toolbar. If you're joining us via the live stream on Facebook, thanks so much for joining that way. We won't be able to respond to your questions in real time, but we'll be sure to follow up to the best of our abilities after the program's finished. If you'd like to connect for a future Science in the Mountains program through Zoom, make sure you sign up over at mountwashington.org. Alrighty, well, before we kick things off to our speakers tonight, I will launch just a quick set of poll questions for those of you who are participating on the Zoom connection here this evening. The very first question of the four that we're asking, where I was curious where folks are joining from, whether you're joining from a state within New England, perhaps outside of New England, or perhaps even outside the country. And then we have one question each from each of our projects that we'll hear about tonight. The first question being, what is the trend of late season snowstorms on Mount Washington? We'll be hearing more about this in just a little bit. Are late season snowstorms increasing, decreasing? Maybe there's no clear trend over time, or perhaps we don't really know. Next question, what cardinal direction do the highest winds recorded on Mount Washington typically come from? And we're giving you all sorts of choices there throughout all the cardinal directions on a compass. So make your best guess. And last but not least, question here from one of our final projects, which model output statistics typically provide the best guidance for forecasting conditions on Mount Washington? So a bit of a technical question here, asking about the type of statistics that come from a certain type of weather forecasting model. Is it the GFS, the Global Forecast Models, the North American model, also known as the NAM, or is it the National Blend of Models? Looks like quite a few of you have participated already. I'll give it just a few more seconds here and we'll close the poll and share some results. So we'll close it in about 3, 2, 1, and we'll go ahead and end the polling there and share out some results. Right now, it looks like New Hampshire is well represented, but beating New Hampshire alone is folks joining from outside of New England. And in fact, we even have someone joining from outside the country as well. So welcome to all of you, no matter where you're joining from. And then let's see how everyone did on the trivia. All right, what is the trend of late season snowstorms on Mount Washington? Pretty evenly split. Very interesting here. Okay. Well, George, you're going to have some explaining to do in just a little bit, I think, to clarify some of those. And then what cardinal direction do most of the high wind speeds come from typically on Mount Washington? Most of you, 30% of you, chose northeast, and right behind there was northwest, and then a little bit of west and southwest. Okay, interesting. And then last but not least, which of those model output statistics provide the best guidance for forecasting? Almost completely evenly split, with the GFS model just eking out one more vote than the NBM. So I'm not going to give away those answers. I'm going to stop sharing that. And for all of you listening tonight who want to know the answers to those questions, well, our speakers this evening will take care of that for you. So first up, I would love to welcome Summit intern George Mousmoules. George, if you're able to turn your camera and mic on. Hey, how's it going?
Hello. Thank you, Brian.
Yeah,
I will
thanks.
share my screen real quick.
Yeah, thanks for joining us tonight. Yeah, feel free. You can share your slides, and as soon as you're ready, feel free to take it away.
Alrighty. So thank you everyone for coming to this tonight. I'll be kicking us off with significant late season snow events here in the White Mountains. So to go over some of the goals of my project, I wanted to establish trends of significant late season snow events both at the summit and the surrounding valleys in the White Mountains, and determine how the intensity and frequency of those events have been changing or haven't been changing over the past few years. And then generate some visualizations to represent those trends and compare them to previous model trends and forecasts in separate studies. So more about that here with my motivation. There have been multiple prior studies done into climate modeling that have tried to depict a picture of how we might be seeing major snowstorms change in their frequency and intensity in the future. And a lot of these have found that in the northeastern US that these storms would continue at the same or at an increased rate. And those that have been based on observational data, which is more similar to the study that I conducted, have also found an increase in general storm intensity in the general northeastern region. So none of these focused on the White Mountains or even New England specifically, but some of them did mention Mount Washington as a specific station experiencing high air in their studies. So I really wanted to investigate how well these investigations had depicted future trends by looking at the past. And first, I needed to get my data. So that data came for the summit from the Observatory B16 daily archives, which is something that our observers use to record all their daily measurements. And those go back very far back in time, so I had a very complete record there. And I chose the Pinkham Notch Visitor Center Station to represent the Notch region of the White Mountains. They record both precipitation and snowfall on a daily basis, along with snow depth records at both locations. Snow depth was used primarily as a sanity check because it is a more subjective measurement based on the person who's looking at it. So really just gauging to see how accurate those snowfall measurements would be. If the snow depth got a lot higher, what did the snow that day match that, and stuff like that. And the period of study included the years of 1995 to 2024 to build a full 30-year climatology. And within each year, I looked at March 1st to June 30th as defining the late season snow events. At the summit, there will often be snow well into June, and especially towards the start of June, there will still be some significant storms that we will experience. So that is why it's extended all the way out to June 30th. Even if the notch doesn't see snow really during that time period, I wanted to keep both stations at a consistent time period. And some locations for those data, if you're not familiar, you can see how close Pinkham Notch is to the summit, distance-wise, but elevation-wise, there's a huge difference between them. So this map gives you a little brief overview of where exactly I focused my study. So for my data cleaning and organization, a lot of this data had to be sorted and represented digitally. So to do that, I primarily used the latest version of Python 3.12, which was able to go through hundreds and hundreds of data points and make sure that they were all accurately represented. And all values of a trace that were recorded by observers were counted as 0 for this project because that measurement is going to be associated with a significant snow event, and it's also rounding down to 0 in this case, and snowfall is rounded to the tenths of an inch. So in this case, for my purposes, it made most sense to round that to 0 to ensure that the trace values weren't complicating any of the code that was calculating statistics. And then for multi-day events, those were manually determined using upper air and surface analysis charts along with radar. I have a couple pictures of some different storms that were multi-day events depicted right here. On the top, you can see a few different surface charts, and on the bottom, the associated radar with that. And by doing that, I was able to gather if there was back-to-back days with significant snowfall, whether that came from one event or two separate ones. So for identifying those 90th percentiles of daily data, I was able to use Python to calculate the 90th percentile for both daily snowfall and precipitation. And those are represented in this image right here on the right. Those are just some of the values. I had a lot more besides that. But days with values meeting or exceeding that percentile were sorted into this new document. And some events, as I mentioned, were split over multiple days and had been overcounted by the code. So I had to, again, manually go in and change that to make sure that it was accurately representing all of the events. And some events qualified for snowfall, but not precipitation, and vice versa. So I actually did the same thing with precipitation and snow as I did with snowfall. And you'll see the visualizations depicting the difference between the precipitation and snowfall events in just a little bit. So defining the significant events were defined based on snowfall. Even though I did look at precipitation, this primarily wanted to look at snowfall, so that is what I used. So it didn't really matter what the pressure of the system was or anything like that, just focused on the amount of snowfall that it delivered. And the systems had to have at least one day where snowfall met or exceeded that 90th percentile mark. And you can see one of the systems that's occurred more recently in 2024. This is the system we had come through in early April. These maps are from April 4th, and you can see the surface analysis there on the top and the radar on the bottom. Some of you may remember this event as giving us a fair amount of snow actually across the entire state, which is somewhat less common, but the observatory certainly got a significant event out of this as well. And there were a lot of different types of systems in the study as a result of using just snowfall. So we had both major nor'easters along with really strong cold fronts and pretty much everything between. So that was really cool to see in the study. And along with those percentiles, I also calculated the running averages of snowfall and precipitation. And on the top left, you can see the rough idea of the equation the code used to calculate those. I calculated the 3 and 5 day running averages, and those were found to contain the longest duration storms along with the most common duration storms, which usually lasted 2 to 3 days. But the code did skip the first 2 and 4 days of each year to ensure that overlapping data did not occur. This really helped in not just identifying the multi-day events themselves, but also when the long duration events were more common. And it sorted those results into separate documents as well, which I generated some separate visualizations from. And with that, we can get into the results. So first off, with the percentiles themselves, you can see this table is representing the statistics that the bar graph is visually showing. And overall, it's about what we'd expect, where you can see that the observatory is seeing roughly the same or slightly more precipitation and snowfall than the notch. The one difference to that being that daily 90th percentile snowfall you can see where the notch actually has slightly more. And that's something that we really were thinking about when we found these results. The most likely reason for that is blowing snow off of these surrounding summits into the notch, causing for slightly higher daily snowfall during these larger events. That's something that can be investigated more in the future, which I'll talk about at the very end. But that was definitely a pretty interesting result we got before we even created any other visualizations. But getting into the core of the study, in terms of the frequency of events, this is showing you the significant snowfall events per year at the summit. And you can see that we did have a few different peaks, the biggest being in 1997, but we also had some in 2017, 2018, and recently 2024. And you can see that the overall trend line is pretty much flat, which is actually indicating a consistent amount of significant events over the last 30 years. So despite the summit seeing a shortening winter season, we are still experiencing roughly the same number of significant snow events in the later part of the snow season at the summit, which is a relatively surprising result. And it does actually align with the climate model predictions that were being shown in some of the prior studies that have been done by separate organizations. So this is a pretty exciting result. And when we look at precipitation events right here, you can see that that matches that trend where we do have some similar peaks. In 1997, we had that peak in precipitation as well. But again, the overall trend is indicating this about the same number of significant events is occurring throughout this 30-year climatology. So again, aligning with those climate model predictions, which is pretty exciting to see. As for the notch, in terms of significant snowfall events, again, we had a few different peaks. Again, very recently in 2023 and 2024, we've seen relatively active years in terms of late season snowstorms. But there's been actually roughly 0.5 more events now than there were 30 years ago. So we're seeing a slight increase in these significant snowfall events. And again, the notch, just like the summit, is experiencing a shortening winter season, especially on the back half of winter. So despite that occurring, we're still seeing a slight increase in significant snow events. So those climate models are doing a pretty good job of showing what trends may be like as we go into the future. As for precipitation events at the notch, those were a lot more consistent, similar to what the summit was experiencing with precipitation events. So again, those observational studies were showing a relatively consistent amount of significant events going into the future, and that is what we are also observing over the last 30 years in the White Mountain Valleys. So that's pretty interesting to see. As for intensity of events, the summit has a lot more outliers, meaning that we're having a lot more larger events than the notches overall. However, you can see that in the notch on the right, they actually had the highest maximum value at 32 inches of snow in a single day, whereas the summit saw 23.7 inches of snow in a single day as its highest over the last 30 years. And there's a couple different potential reasons for that. I mentioned the blowing snow into the notch being the most likely. And then on the other side of that, at the summit, it can be difficult for snowfall to stick around for extended periods of time due to the strong winds that we'll frequently observe in the wintertime. So that maximum amount of 23.7 inches may well have been very higher, but the wind blows that snow into the notch, so they get a slightly higher recording. And that's something that definitely factors into this study and needs to be investigated in the future, but that's definitely an interesting thing to see here. However, for the majority of daily snowfall events, they will produce between 6 and 10 inches of snow in both the summit and the valley. So that's the pretty standard intensity. However, that Q3 value is right at about 10 inches for the summit and 11 inches for the notch. So again, we're seeing pretty consistent trends over the last 30 years in that most of the storms are falling between those values and the minimum, which is 5.5 at the summit and about 5 at the notch. And then results for the precipitation are kind of the opposite in that while the summit still has more outlier events, the summit does have the highest outlier at 6 inches, whereas the notch has a highest at 3.4 inches. And I know that some of these numbers are kind of clustered together because the code didn't play too nice with me, but I can still interpret them for you guys, which is great. That minimum for the summit being at around 1 inch, and also the case for the notch. And the median values of 1.2 inches at the summit and 1.3 inches at the notch indicate that both are seeing about the same high intensity events. So that's about what we can expect in the largest events that will come across this part of the state. And then for the duration of events. So this, you're looking at the 3 and 5 day running averages in terms of the amount of days that recorded 90th percentile snowfall in this graph. And years that saw more events also saw more longer duration events. That blue line has much higher peaks than the 3 days. So we see more events where they're lasting up to 5 days. Whereas in the years that we're seeing slightly lower snowfall or significant snow events, that 3 day data line is staying right around where the blue is, if not slightly higher than it in some years. So that's something that's pretty interesting to see at the summit. And then in terms of precipitation, it followed the same trend with snowfall, where the summit experiences more snowfall events than precipitation days. However, when we have more high intensity precipitation events, we also see those events last longer. So that's something that's pretty interesting to see, and a result I was actually not expecting to get out of the study. So that was a huge bonus. And then I also looked at the notch for the statistics, and you can see there's a lot more variation in the notch. There's a lot more years that experience 0 days that experienced 90th percentile events. However, the years with more events did again see longer duration events in terms of snowfall and in precipitation right here. So it didn't match with snowfall as well as the summit's precipitation matched with snowfall, but again, it supports that years with higher frequency in events also had longer duration events. So I was able to get a lot of great conclusions out of this study. So a steady rate of significant snow events is being experienced at the summit over the last 30 years. And significant snowfall events are actually slowly increasing in Pinkham Notch. And that's supported by climate models that have been developed in outside studies. And there's also frequent changes in the number of events per year, with a surge in events in the last couple of years. It's also more likely that storms will last longer in more active years. And it's also seemingly likely that Pinkham Notch experiences some effects from blowing snow off of the mountains. And there's a lot of different angles this research can be taken in the future. One being identifying the causes for increases and decreases in the significant events of different years. That can involve looking at things like El Nino and La Nina patterns, along with the changes in the jet stream pattern and how those storms are arriving to this region. Also, utilizing alternative event methods for identifying events besides just a 90th percentile and running averages. Expanding the data set further back can also generate more significant trends, along with including more stations throughout the White Mountain region to gain a better picture of how the overall region is experiencing these changes, not just the Mount Washington area locally. And performing case studies on some of the highest precipitation and snowfall events to see why those events were so much stronger than what can typically be expected, along with, again, investigating those effects of windblown snow into Pinkham Notch's measurements. And with that, I want to thank you guys all for taking the time to listen to my presentation tonight, and any questions can be answered at the end. I will turn it over to Maya to give us her presentation.
Okay, hello everybody. Welcome into Science in the Mountains. My name is Maya. I'm another intern here at the summit on the Mount Washington Observatory. And my presentation is loading right now. All right, so this summer I've been focusing a lot of research on the significance of our wind events and our recorded instrumentation values of wind on the summit of Mount Washington. As we know, Mount Washington has some of the most extreme weather on the entire planet. And so furthering our understanding of what's going on with the winds up here is really great at helping us understand some summit conditions, as well as how the general atmosphere is working in the Northern Hemisphere. So it's really important that we're really looking at these numbers and trying to discern what they say. All right, so some things to gain from the analysis of these trends and why these trends are important, not just to look at the numbers, but to kind of read further in. So first, there's a constant change in the infrastructure and everything that's going on the summit. So there have been a lot of buildings that have been built, a lot of buildings that have been demolished, a few radio towers up there that once again have built in to be demolished. Every single day, there's a different number of vehicles atop the summit. And so all of these things are going to be influencing our wind field. So it's going to be influencing the dynamics of where things are coming from and where they're going. Another thing is that our anemometers, the instruments that we use to measure the wind, they've changed locations since we've been opened in 1932. They've actually moved 4 different times. So it's important to take that into account, that we're measuring winds from 4 different locations. Another issue is if we are to just straight analyze the data, there's a homogenization difficulties, considering the fact that there's so many changes going on with the wind data. And lastly, our standards of measuring wind direction were completely different. So it's a lot of changes that we've gone through since 1932 to get more accurate readings and also to comply with National Weather Service standards. So. All right. So for those of you who aren't super familiar with the infrastructure on the summit today, this isn't going to be too helpful for you because this is what the infrastructure on the summit was in 1935. So the red little star that you see is where our anemometer used to be. And that old building right on top of it is our old observatory building. And so you can see that the infrastructure is pretty much so that there's not any significant blockage of wind that's going to be hitting our anemometer. Our anemometer was about 22 feet off the ground, which was above the height of the building right there. So didn't have too much obstruction. And in the beginning years, we were seeing about 57.6 what we call big wind events every year. A big wind event is what we consider a event in which winds are sustained over 100 miles per hour. So that means the average winds over every minute, averaged over every hour, are over 100 miles per hour. And we're seeing about 58 big wind events per year in the early days of the observatory. And then once we move on, which is on the next slide, we can see the development of some other buildings that we're going up here. So significantly, we have this L-shaped Yankee building. So the Yankee building is about 25 feet at its highest point. So it's actually blocking the height of the anemometer that we see, which is that red little star again. And these arrows in size and direction represent the majority of winds that we're seeing. So for those of you who answered the question saying that the majority of our winds are coming out of the west, that is actually pretty correct. So west and southwest are where the majority of our winds come from. And you can see that the L shape of that building is actually hindering our anemometer from receiving those winds. Our second highest winds are coming out of the northwest. And so you can see once again that the L shape of that building is really in the way for the little star where our anemometer is. On to the next slide to see what it looks like today. So you can see that little L-shaped building right there, and the red star is where our anemometer used to be, and the yellow star is where our anemometer is now. So on top of the Sherman Adams building on that tower, we stand about 1/10 of a mile away from the old location. However, we are about 20 feet higher than the old location. So we don't have as much obstruction from the wind, but it's also important to note that we are pretty significantly to the northwest, whereas our old anemometer location was a little bit more southeast. So. All right, and another discrepancy that we have with our wind directions up here is changing to fit National Weather Service standards. Prior to 1968, we used 16 directions. So that's including more specifics like north, northwest, east, northeast, situations like that. But now, after 1968, to comply with the National Weather Service, we only use the 8 cardinal directions. So anything that would have been measured north, northwest is now either going to be put into the north or into the northwest direction. So that's really important to take into account. And what do these mean for the future changes? So why is it important that we're looking at everything that's kind of funky with the data? So all of these summit infrastructure inconsistencies shows that homogenization is something that really needs to be worked on. And it shows that we can't necessarily just look at the data and come up with a story from the data without knowing the exact dates of the wind fields and when they existed. Each set would need to be scaled. So a lot of times when people are analyzing the winds, or at least how the winds have been analyzed in the past, they've been analyzing them from 1941 until 1980. And then when the anemometer moved at 1980 until present day, that was 2 different sets. However, there were a lot of changes going on between 1941 and 1980. The anemometer location change was not the only difference in our data collection. And so it's really important that we make sure that we were to split up those data sets into every single time a different structure was going up or down. And then those sets would have to be scaled to a control. The only issue is that we don't have a control set. So there's not really an easy way for us to all pretend that everything is nice and under the same conditions, because really they weren't under the same conditions. And another thing that we have to work on in the future is figure out how we're going to change those 16 cardinal directions into 8 cardinal directions. So. All right, and then we'll go on to look at the data. So even though there are some of these discrepancies that we have, it's important to notice what the data is showing us. So you can see from 1941 to 1980, there appeared to be significantly less big wind events as there are now. So there used to be, on average, 7 big wind events per year at the old anemometer location when that Yankee building, the L-shaped building, was kind of hindering the wind. However, we can't say that for a fact. We have to say that we can only assume that. The only way to check that would be to knock down the Yankee building and kind of test out things from there, which we unfortunately don't really plan on doing. But we can see that from 1981 to 2023, we've had a lot more big wind events. So the average number of big wind events today is about 16.58. So we're having about 17 big wind events per year. And you can see that there's a pretty steady decline in our big wind events that are happening. However, it is important to note that the anemometer that we used from 2011 to 2019 had significant flooding issues and often didn't record winds that were in excess of 100 miles per hour accurately. So that's just another important thing to note. But other than that, the trend is showing that we are losing our big wind events, and in this 40-year time span, it's starting to look like we are going down as the windiest place on Earth. So move on to wind direction. And so here is kind of a visual description of what you all were guessing earlier as to where most of our winds come from. So you can see that about 50% of our winds come out of the west, both at the old location and at the new location. However, you can see the major difference is in the northwest. So right now we receive a lot of winds out of the northwest, whereas from 1941 to 1980, which is the graph on the left, we received significantly less winds out of the northwest and just a little bit more winds out of the southeast. So that little southeast bump could mean one of two things. It could either mean that there was an eddy being created from the L shape of that building, kind of swinging winds around from the back and giving us southeast winds, or it could mean that where we are now on top of the Sherman Adams building, we are having some sort of blockage of southeast winds, which would make a little bit of sense considering that our anemometer location is now about 1/10 of a mile to the northwest. So all important things to note here. And then I'll just go over some conclusions that we have. So here you have a little historical photo on what the observatory used to look like and how winds have changed since then. So in conclusion, we have the wind field's been changing quite a bit in the past 90 years or so. And the movement of the anemometers definitely gives us a kind of new perspective on what's going on with the winds. And we need to remember that we're measuring different winds when we put the anemometers in different locations. The changing of the wind direction standards is very important as well. So it's important to look at how those wind roses are turning out. And from what we can see that there appears to be a decline in the big wind events, and that we're also seeing a significant shift in wind direction out of the northwest. So that's what I have on the wind analysis. If you all have any questions, feel free to use those in the Q&A and we'll answer those shortly. And without further ado, I will introduce the other two interns who are working together, Josh and Jacob, and they'll give you a little rundown on their project this summer.
Thanks for the presentation, Maya. Good to see you.
Of course.
I'm Joshua Elms. I'm one of the summit interns here at Mount Washington. I just graduated with a degree in data science from Indiana University, and I'll be going back for a master's in atmospheric science from the same school in the fall.
I'm Jacob Garside. I go to Plymouth State University just down the street from here. I'm going to my junior year of meteorology there.
And today we're going to be presenting on the effect moss has on mountain weather forecasting.
So mountain weather forecasting, why is it important? So as some of you may know, Mount Washington produces 2 forecasts daily, one at 4 a.m. and one at 4 p.m. And to do that, we use weather models and all kinds of stuff like that. But unfortunately, weather models are grid-based. And Mount Washington, they have kind of a small resolution, or they have a big resolution, not a small enough resolution for Mount Washington. So if you look to the right here, you can see this image. This is actually a pretty good representation of what's going on. You have a point A, a grid point that's pretty far away from us at about 1,000 feet, and a point B that's at about 2,000 feet of elevation gain. And that's only about 1,000-foot difference between those 2 points. And that's what the model sees compared to Mount Washington right there at 6288. That's a 4,000-foot difference. So the model completely glazes over mountain weather. So when we're forecasting, we can't just rely on those physical weather models. We have to use forecaster experience and model output statistics, which is what Josh is about to talk about.
Model output statistics is a very long acronym, but let's break it down. So it's essentially the same process that humans use to learn, you adjust from all of the forecasts you've ever seen for the lower elevations, and you learn by experience how to go into the mountain weather that we would see at Mount Washington. So for example, you might know it's on average 30 degrees cooler on Mount Washington than it is in the parts of the valley that the gridded forecast is valid for. But instead of using human intuition accumulated over a lifetime, this is a mathematical way to do it. The steps are to collect a bunch of gridded model data. And here you can actually see we have a sample grid that's a 1/4 degree resolution. So if the entire Earth has 360 degrees of longitude wrapping around it, this is a 1/4 degree, so 1/4 of those. And you can see this grid placed around with temperature forecasts at each grid point around us. Now, you can use observational data that we collect here at Mount Washington to form a statistical relationship between all of the gridded forecasts around us and the actual weather we're experiencing up here on the summit. And once you find that relationship using a technique called linear regression, you can actually apply that forward in the future. So if you've trained it on the past of all of the forecasts and the conditions we've seen after those forecasts, then you can use future forecasts and fit those to our Mount Washington weather. And on the right, you have an example of this. Maybe the model says it's going to be 82 degrees in the valley, 75, 80, and so on. All of those numbers, those forecasts, get fed to a MWOBS algorithm that learns how to adjust them to Mount Washington. And then we produce a forecast that says, for example, 53 degrees Fahrenheit. Some of the pros of the MWOBS are that it's very easy to compute. In the age of big data, where everyone is worried about neural networks and exascale computing, this is a complete reversal from that. And that's because MWOBS is, in computing terms, an ancient technique. It actually was first used in the 1970s, and it's been in use operationally ever since then, still in use to this day. It also uses our observations really effectively, which is good for us because we are an observatory with a 92-year climate record. So if we can take advantage of that record and leverage it for future forecasts, that's really effective. However, it's got a big downside, which is that it's not physics-based. It doesn't fundamentally understand the actual science and processes going on in the atmosphere. And so it could make a forecast that says there's 150% relative humidity one day. The problem with that is relative humidity is what percent of the water that the air could hold is it actually holding. So that's saying the air is currently holding 50% more water than is possible. It's a nonsense forecast and no human would ever make it, but because it's not using a physics scheme, it's just machine learning, then the MWOBS could totally make that. There are ways to get around it though, such as adding a threshold to the forecasts it can produce.
So to talk about a little bit of the data here, when we're doing this project, we were using the GFS MWOBS, the NAM MWOBS, and the NBM. The GFS stands for the Global Forecasting System, NAM stands for North American Mesoscale Model, and the NBM stands for the National Blend of Model. The GFS MWOBS and the NAM MWOBS are each using just one model in their MWOBS algorithm, whereas the NBM is using over 30 models in theirs. Our period of study goes back around 4 years from November 1st, 2020, all the way to May 16th of 2024. We ended there because the NBM was actually updated in May, and we wanted to keep our MWOBSes the same throughout our entire time period here. We also used a bunch of different lead times, about 22 different lead times. We went from 6 hours to 72 hours at intervals of 3 hours. When I'm talking about lead time, if I were to say I'm forecasting out 48 hours, that would be a 48-hour lead time. If I'm forecasting out 24 hours, that's a 24-hour lead time. You can see all of our variables here on the right that we were looking at. We were looking at temperature, dew point depression, wind speed, and wind direction. Most of those make sense. Dew point depression might be a new one for people, so I'll break it down for you. Dew point depression is just basically temperature minus dew point. It shows the difference between the two, and that's really important here on Mount Washington. We're in the clouds about 60% of the year. And to forecast for those clouds, we use dew point depression. If the dew point depression is from 0 to 5 degrees, anywhere in there, that shows that there will likely be clouds on the summit.
Let's talk about the actual quantitative metrics we're going to use here. So the standard for this really comes from the National Weather Service, or NWS, and they have two primary numbers that they're going to report to show you how good their forecasts are. The first of them, called the MAE, or mean absolute error, we have the equations on the right. Don't worry about it if they don't make sense. We'll talk through a common explanation of it. The MAE, the most important thing to understand, it means how far off is the average forecast? Not in terms of direction, just how much error is there between your guess and the correct answer on average. The bias is similar, but it answers the question, does the model systematically forecast high or low? For an example, if a model tends to over forecast temperatures, call them hotter than they actually come out to be, that has a high bias, and vice versa for low biases. So I'll show you these two metrics throughout the following figures. Let's talk temperature first. Obviously, we did analyze 5 variables, but in the interest of brevity, we're just going to stick to temperature and wind speed for my side of the presentation. Here on the top, there's a lot of information, but to break it down, the GFS is our red line here, the NAM-MOS is the yellow line, and the NBM is the blue line. So each of these 3 lines is shown for all of the lead times from the left at 6 hours to the right at 72 hours, meaning this is going into the future. And the y-axis is the average error. So mean absolute error on top and bias on bottom. Temperature is pretty straightforward. We can see that all of the models perform similarly, around 2 to 3 degrees of MAE early on in the forecast, out to 2.5 to 3.5 degrees by the end of the forecast. For context, those are fantastic errors. If our forecasters consistently produced 2 to 3 degree forecast errors, that would be a very good result, because that's telling hikers within just a couple degrees of accuracy what conditions to expect up here. So these are all very good results. You can also see that their biases are small. Even though the scale here makes it look like there's a pretty dramatic trough in the NAM bias towards the end of the lead times, these are all under 1 degree. So 1 degree of bias is totally acceptable in weather forecasting, especially given that these are all slightly under that as well. It's pretty simple for temperature. They all do similarly, but it's not quite the same for wind speeds. In wind speeds, you can see that the GFS and NAM, these 2 lower lines, actually outperform the national blend of models pretty significantly, having about half the errors at a given lead time as the national blend of models does. This is something the developers know about. They are going to be releasing a new version. Actually, that's the version that we cut off our study for, but we'll talk about that in future work. Here, though, you can see the current versions of the national blend of model are definitely underwhelming when it comes to wind. Not only do they have higher MAE than the other models, but they're actually the only ones that exhibit a really strong bias from 2 to 4 degrees high. So that means they're consistently over forecasting Mount Washington's winds by between 2 to 4 knots, which is roughly 2 to 4 miles per hour.
So my piece of this project was to look into some case studies of particularly big errors that these models made. We could have looked at quite a few of these. I picked the top 5 errors and made plots for the top 5 errors for every variable and every MOS variant that we were looking at. So we ended up with 75 plots. I'm only going to show you 2. But just remember that these actually represent a lot of what's going on in the other plots. I tried to pick the best representative plots for these. Again, I was looking at 5 variables: temperature, dew point depression, wind speed, and wind direction. But today, in the interest of time, I'm only going to show you dew point and wind speed. So here's wind speed. I'm really going to try to break this down for you looking at these plots here. So in this plot here, the darker colors are higher wind speeds. You can see that yellow star there is Mount Washington. You've got about 85 knot winds over that area. The lighter colors are either no wind speed or very little. You can see here that there's a very large low pressure system. In meteorology, a low pressure system is associated with bad weather, storms, things like that, whereas a high pressure system is associated with blue skies. You can see a counterclockwise rotating low right here, coming right over Mount Washington with kind of the strongest winds focused right on Mount Washington. You may also notice that there's some barbs on this plot. Those barbs are where the wind is coming from. They're pointing to where the wind is going to. So if you are looking at some of the barbs right over Mount Washington there, they are coming from the south to the north, or from the southeast going to the northwest. Now, when we were looking at this plot, the GFS MOS actually made an error of 44 knots in this forecast. So you can see that day there was about 85 knot winds. It was off by 44 knots. That's about 50 miles per hour. The NAM MOS was also off by 35 knots when making a forecast for this day. That's about 40 miles an hour. This is a big deal for hikers, or just the safety of people. If we're forecasting and basing our forecasts off of the MOS and it's off by 50 miles an hour, that's a bit of a big deal. The next one that we're going to look at is the dew point. So like I was saying earlier, we have high pressure and low pressure systems. This is a high pressure example. You can see that big bend going all the way across the United States from down in Texas all the way out to the Atlantic Ocean there, kind of peaking right over Mount Washington. Now, again, high pressure is usually fair weather skies, things like that, lower winds, which you can see there with about 30-knot winds. And this was a big day with dew point errors in the forecasted dew points. The NamMOS made an error of 42 degrees, which is a pretty big error for dew point. It took us a little while to figure out exactly what was happening here, and we think that it's because we're in the clouds most of the time, 60% of the year, and if the MOS is forecasting us in the clouds and those clouds lift or drop below the summit for even a little while we are taking an observation, that can completely change those errors. So we think that's what happened on most of these days, was that we were in the clouds and we were forecasted to be in the clouds, and then those clouds either lifted or dropped below the summit.
The primary purpose of this study is actually to provide some very simple conclusions for forecasters up here on Mount Washington. It's useful to know all of this in an academic sense, but we want it to be operationally important for forecasters. They should be able to know which version of the MOS is going to be most effective for whatever the task is. So we've broken it down by variable group. For temperature, dew point, and dew point depression, this is the ranking roughly. The GFS is slightly better than the NAM, which is slightly better than the NBM. But importantly, they are all comparable in terms of error. If you have a good reason to be using one over the other, go for that, but they're roughly similar. Not the same story for wind speed and direction. Currently, the GFS and NAM are significantly better than the NBM. So in a future document for forecasters, it'll be noted that it's not wise to use versions 4.0 and 4.1 of the NBM to forecast winds.
And for forecasting wind speeds, it's important to look at high wind speeds and winds from the south. I forgot to mention that when we were looking at that plot, most of those winds were from the south. When you have winds coming from the south, southeast, or southwest, Mount Washington isn't used to that. If you remember back to Maya's project that she was just working on, most of our winds are from the northwest or west. We have the opposite here. When winds come from the south, we don't have a very long observational record of that, and the MOS doesn't function very well when we have winds coming from those southerly directions. When forecasting dew point, it's important to try to forecast or try to look out for brief clearings that might happen. If those clouds again go below the summit or above the summit, the dew point can change by tens of degrees very quickly.
There's also a good bit of future work to be done, even given the amount of work that we did in this study. First off, there is a new version of the NBM coming out, version 4.2. And that means that over the next year, we're actually going to be looking out for all of the forecasts from NBM version 4.2. If those forecasts for the wind are pretty good, it might be worth doing another verification study to figure out whether they've improved their wind forecasting capabilities. And maybe the picture is different now, and version 4.2 is better than the GFS and NAM for wind forecasting. There's also a few more variables we can look at. When I say probabilistic variables, I mean things like probability of precipitation or probability of a thunderstorm. These are verified a little bit differently than the metrics we've showed you so far, but it could still be really useful to be able to use the MOS for forecasting those. Of course, we also have visibility is quite important up here, and especially temperature extremes. So those will be minimums and maximums, or daily highs and lows. Those are some of the biggest products we put out during our forecasts, so it'd be useful to actually show those extremes in the verification. Finally, we know that the different MOS varieties actually have different equations during the summer and the winter. So it would make sense to break down the study by season. During the summer season, we should have one set of conclusions, and in the winter, there could be another. For an example of why that might be useful, perhaps that issue with the southerly winds being underrepresented is only a summer problem. Maybe we just don't see those as much during the summer, so you don't have to worry about that as a forecaster during the winter. There's quite a bit of work to be done though, and hopefully Mount Washington is able to take on that project.
Thank you guys for listening. I think we're going to turn it back over to Brian. Thank you so much.
All right, thanks so much, everybody. Thanks, Josh. Thanks, Jacob, Maya, George. Feel free, pop your camera, your microphones back on. We'd love to see your smiling faces, because we do have some questions for you that I know some of you have already started answering some of the chat, which is great. For those of you who are joining, on Zoom and have some questions for our intern researchers here, feel free to use the Q&A button. There are already a few questions that we have, and by all means, as they bubble up, we'll try and get to as many as we can, and certainly can answer any questions that come up after the fact here. Question here, let's see. Oh, so many that I know a question that had come up earlier from Ken, who was asking just for a little more background actually from each of you, which I know George, you're able to share in the chat a little bit about where you're from, but I was wondering if maybe just in the order that you all spoke, if maybe just give a little more background about where you're from, what brought you to Mount Washington, and your course of study, if you didn't already mention that a little bit, that would be really interesting. Maybe starting with you, George.
Sure. Yeah, so I am currently going into my graduate year at Plymouth State University this fall, which I'm excited about. And that's also where I got my undergraduate degree. So excited to be going back there. And originally, I am from Southern California, but I've lived in Southern New Hampshire for most of my life at this point. And I've definitely gotten my fair share of New England weather. So
Thanks, George. What about you, Maya?
Hello, my name is Maya Hartley. I'm originally born and raised in Rhode Island, so also have my fair share of New England weather. However, I never quite made it up to New Hampshire to experience, the real things that Mount Washington has to offer until this summer, the beginning of the internship. For the past 4 years now, I've lived in Honolulu studying atmospheric sciences at the University of Hawaii-Manoa. So a lot of my expertise in the past has been Pacific centered, which is significantly different than what we're seeing up here in New England, especially on top of mountains like Mount Washington. So it's really great to be able to learn from new perspectives as much as I can.
And Josh, Jacob, I know you guys shared just a little bit, but anything else you'd be willing to share about your personal pathways?
Yeah. So I'm Josh Elms. I actually, like I said, I'm going to Indiana University, and it wasn't until about 1.5 years ago that I saw an announcement on the news that was like stratosphere is actually on the surface. There was a point on the planet where it was in a different layer of the atmosphere at the surface. And I had learned a little bit about atmospheric science, and that was just enough to pique my curiosity. And so I look into it, and it's a place called Mount Washington. I'd never heard of it before, never come around here. Look into it further, realize they have internships, and I knew instantly that I was going to have to do 2 things. 1, I was going to have to work at Mount Washington, which means that 2, I was going to have to actually add atmospheric science as a minor so that I could even apply for the internship, because I was in data science until that point. So I had no reason to apply yet. But it's been great to meet everybody here and see some of the extremes that I was looking for.
Yeah, so I'm from Plymouth State University. I had said that I'm going to my junior year here, and I've actually been applying for this internship for quite a number of years. I had no idea what went into it, so I think as a sophomore or junior in high school, I was like, I'll apply, which I have to imagine got thrown out immediately, which is pretty funny. I've always wanted to be up here. I've been obsessed with the White Mountains with bad weather all my life, and I'm just so glad to be up here. I had met some of the observers a few years ago after that -47 temp. And I was obsessed with asking them questions and understanding what was going on. I even saw one of our observers who's up here right now, Carl, at a museum that I was working at last summer, and I almost asked him for an autograph. I was totally fanboying. I ran over to him, and he was a little taken aback. He'd never been recognized before. So I've just always been obsessed with it up here, and I'm really glad to be here.
Well, that's great. Well, obviously for those who know, they know. Really appreciate you all sharing a little bit more of your backgrounds, because you all just represent a huge pool of really fantastic folks who've come through the observatory through the internship program. There's some other great questions here, and Maya, I know you had kind of hinted at this in your talk, but Ken was asking a question about, hey, maybe instead of knocking down Yankee Building, is it possible maybe to create like a computer model that might quantify the impact of Yankee Building on the anemometers historically or something like that? Or maybe we do just need to wait until that building, gets reconstructed and we got to pop a anemometer up over there to try and measure differences. Oh my, I'm sorry, you're actually muted right now.
Sorry about that, everybody. Okay, so as Josh and Jacob had said, computer models are a little difficult to kind of accurately depict what's going on the summit of Mount Washington. So until we get those developed, our plan for now is to hopefully get some anemometers up in the old locations to compare them. However, the pitot tubes that we use are pretty exclusive. So we only have 2 other pitot tubes that are not in use right now on our summit. And so those are the only 2 we have to use. And one of those just happens to be in Antarctica and the other one happens to be on Mount Everest. So that's really the technology that we would use. And we do plan in the next upcoming years to further this research with maybe trying to bring those anemometers to less extreme locations and put them right back to the old Yankee building. So right now that's what we have in the plans, but the research in Antarctica seems to have taken the front on that. So.
Well, and since you mentioned it, that was one other question I had. I know you hinted at the changes in anemometers and the technology over time. I guess maybe if you could speak to that just a little bit more, just obviously it's not comparing apples to apples, I guess, with when you're, using one anemometer technology perhaps over another. Is that sort of true?
So the pitot tubes actually began to be used in 1938. So they are pretty old and the technology is simple enough that we haven't really been updating them too much. The difference between the models has been really minuscule, and it's usually in terms of how they get pumped or really how long their wires are and what they're connecting to. So we've had pretty steady analysis in terms of what the anemometers are, which is great for us. So we don't have to put too much information into that, too much focus on the changing of the technology, because we kind of are using ancient technology, even though it works really successfully up here. So.
Well, it's great, the consistent approach, and certainly for temperature, a little bit more straightforward when you're just using literally the same type of glass thermometer with either alcohol or mercury in it. So awesome.
Yeah, we definitely try to focus on actual things as much as we can up here. So.
For sure. Thanks, Maya. George, I was just kind of curious. I know you spoke to it a little bit, and I know there was some comment from Rick as well in the Q&A just around the number of late season snowstorms and what that sort of looks like. And the fact that you said there's either some change or a little bit of an increase, particularly down at Pinkham Notch in these late season events. And that's happening, yet at the same time, there's sort of like this shortening winter season window because of a warming climate. And also sort of what we know from other research, basically like the Swiss cheeseification of winter, and that we have these really big rain and melt out periods. So I guess the question is, both things are true then, huh? We can both have big rainstorms and meltouts, but also late season snow events. And at any rate, yeah, I'm curious how much you were sort of thinking about the relationship between those two.
Yeah, we definitely can see both. And especially in more recent winters, you talked about how the winter season has been changing so much. A lot of what we've been seeing is really strong batches of cold air coming down from Canada, and then really rapid warm-ups where we have those meltouts that you were talking about. And a lot of those larger systems that will come through will end up producing more precipitation than snowfall. So we're able to see both large snowstorms at one point in the winter and large rainstorms at other points in the winter. So that's part of what we were looking at for sure. And that's why you're seeing differences in the amount of precipitation events and snow events on a yearly basis. They're not just following each other exactly. And so that's definitely something that I had looked at. There's some separate research projects going on that are being taken on by some of our observers that look at that aspect of rain on snow and snow liquid precipitation ratios more closely. And that really inspired part of the project as well. So that's definitely a whole nother aspect of the study that really I found pretty interesting and motivated me to conduct it.
Yeah, and you got me curious also, like you said, bringing in some other stations around the region. I would love to know some lower elevations like here in North Conway, using some of the data to see what that looks like. Because technically we had a normal by the numbers snowfall season, just in terms of total accumulation, but it doesn't mean there was a lot of snow on the ground for a long time here in lower elevations.
Yeah, that's exactly right.
Yeah, yeah. And that's just one winter anyways, anecdotally. Josh and Jacob, was curious because I know you guys also mentioned this a little bit when it comes to, I was so curious about the advances of, I guess, probabilistic forecasting over time and the increase in just general accuracy of forecasting, specifically like the longer the lead time, we've gotten a lot better. We as a broader meteorological community, I think the Washington Post just put out this like cool article not so long ago that was looking at like long term, the real improvements of forecasting over time across the US. It made me just wonder, like you picked like a pretty selective like sliver of time. What was it, was it the last 5 years, right? Yeah, and I was curious like how much, why you selected, I guess, that period, and like how much like improvement there might be over time, because I'm curious, like, are you guys proponents then? Should we be doing more than a 48-hour forecast on the summit of Mount Washington?
I can speak to the piece of this that I know, and then Josh can take that. We used 4 years because that's all the data that we were able to get from some of the MOS variants that we were looking at. We weren't able to get data going further back than that, and further back than that, they changed to a different version of themselves, and we wanted it to be more accurate to what we've been seeing in the last 4 years. As for forecasting and model output and everything like that, it's come a really long way. I have professors that it didn't exist when they were meteorologists, back when they were going through college. So it's really gotten a lot better.
As for whether we can do a 72-hour forecast, that's an ongoing topic of discussion at the observatory, but this study was sort of intended to address part of that. And if you think back to those figures we showed, you didn't see some incredible jump in errors that occurred after the 48-hour mark, which is an indication that we have similar skill in terms of forecasting between 48 and 72 hours as we do between 24 and 48 hours. So it might be possible to go out to a 72-hour forecast window given how skillful our models are currently.
Interesting. I caught that too. It made me very curious. And well, I guess we'll have to wait and see, because that is definitely an interesting topic, and for folks maybe on the outside looking in a little bit curious about, the forecast process and what that looks like. Certainly encourage you to reach out if you have thoughts about the forecasts and how we can continue to have it be a tool for informing the public, and obviously for public safety and awareness. I know we're a little bit past 8 o'clock here. We have just a few more questions, some nice shout outs from some summit volunteers who've gotten a chance to meet you all this summer. Shout out for the Plymouth State representation, and not to leave anybody else out here. But I'm just kind of curious from each of you, if put you on the spot a little bit, if there's just sort of maybe a favorite or a highlight of sorts, perhaps from your internship this summer that you'd be willing to share, just to kind of highlight what the experience has been like for you personally as an intern. And George, maybe I'll put you on, and we'll go around the horn once again, if you don't mind.
Yeah, that's fine. No problem. Besides all the research that I was able to do, I definitely loved getting to experience firsthand some of the extremes that the summit sees. Two of the highlights for me was getting to be in a microburst during a thunderstorm that came across the summit back in June. And then a second being getting to experience 96-mile-an-hour winds, so Category 2 hurricane force winds at the summit, which is something that I've never been able to experience before. So getting to experience those extreme conditions was definitely a highlight for me.
Thanks, George. What about you, Maya? What comes to mind?
I know that Mount Washington is not necessarily known for having the best visibility, as we are in the clouds about 60% of the time. But when the visibility does clear up, those are definitely the most memorable events. We've been able to watch quite a few meteor showers up atop the summit. And I know that this past week, even though I wasn't up there, we got some pretty incredible views of the aurora borealis. So just all of the astronomy side of things that goes on up there is really incredible. And also being able to watch the fireworks that everybody down at the base was setting off. It was pretty cool view to be higher than all the fireworks. So
yeah, definitely a unique perspective for sure for fireworks, and even though aurora. All right, so last but not least, Josh and Jacob. All right, I guess you guys got to see some pretty cool aurora last week. Anything else come to mind?
To be honest, I'm a sucker for the sit down dinners, just being able to talk with everybody up here, joke around. That's like the hour a day where we have both the day shift and the night shift, colliding along with our volunteers. So I've loved getting to meet everybody and really know them at the dinners.
I've got two, one weather related, one not. Something that happened this week, we had a 105-mile-an-hour wind gust, which I was standing on the edge of the mountain for in my rain gear, and it blew my rain jacket open, and I was screaming and yelling. It was awesome. It was just really, really cool to see. It was pouring rain. It was like needles on my face. It hurt so bad. And the other one would be this little point called Goopher's Point that overlooks the Southern Presidentials, and Josh and I like to sit there after a long day, or even in the middle of a long day, and just hang out there. And some of our best moments have actually been in the fog. Just staring up at the fog. It's really nice to just relax and not focus on anything else.
Oh, I love that. I really appreciate that. Thanks to each of you for sharing, and really appreciate the time that it took. Just a little background for everybody. Our interns here produce these great projects. They you might have already met some of them, giving a tour of the weather station. That's one of their large responsibilities, introducing the public to the work of the weather station here. Supporting a wide variety of other aspects of the mountain, including also getting to try their hand at forecasting every day and all those other pieces, all those other responsibilities we haven't mentioned here. We're certainly really grateful for everything you've given us this summer as you wind up your last shifts here. So we thank you for that, and certainly wish you well on your next step here, and hope you're not too far away, and at least stay in touch. But thank you. Thanks for presenting your work. I know you've already presented it to our science committee, who helps support and mentor some of these projects as well. So I'd like to give a shout out and thanks to all the volunteers and our trustees who help make that happen as well. And then last but not least, thank all of you for joining for tonight's program. If you enjoyed tonight's program, we'd like to encourage your support, certainly to keep free programs like this free. If you'd like to make a donation to support a program like Science in the Mountains, feel free to hit the donate button over at mountwashington.org. If you have thoughts for tonight's program, for our speakers, any feedback whatsoever, any suggestions for future programs, please take some time to fill out the survey that'll pop up in your Zoom window following this program, or in the follow-up thank you email that'll come through Zoom as well. And then last but not least, don't forget to join us for next month's Science in the Mountains program. That'll be on Tuesday, September 24th at 7 p.m. We're going to be hosting astronomer William Grundy from Lowell Observatory in Arizona. He's going to be discussing extraterrestrial weather and climate. So don't forget to register for that program. And if you've missed any, want to watch those recordings, feel free to visit us over at mountwashington.org or on our YouTube channel. All right, thanks everybody. Thanks George, Maya, Jacob, Joshua. Have a great night, and thanks so much all of you for joining. Take care.